Hello, everyone. Thank you so much for joining us today. My name is Vijay Injam. I'm Senior Solution Architect with Amazon Elasticast team.
Hi, everyone. Thanks so much for joining us today. My name is Krishna Sarabu. I'm a Senior Database Specialist Solutions Architect specialized in Amazon RDS PostgreSQL and Amazon RDS Aurora.
Thank you, Krishna. So, in my current role and also in my previous roles, I spend a lot of time working with customers who are migrating their applications from monoliths to microservice architecture, or in other words, modernizing their applications using Amazon services. And I see services like EKS, Amazon MemoryDB, and Amazon RDS for PostgreSQL play a prominent role in this journey. With our experience, we collaboratively bringing you today's topic, which is modernizing your application using RDS for PostgreSQL, Amazon MemoryDB, and also containers. And our goal for today's presentation is to provide you with enough information so that you can take informative decision while building or modernizing your applications using AWS services. As for the agenda goes, for the next 30 minutes or so, we'll talk about characteristics of modern applications, followed by a case for modernizing your application, or in other words, move to microservices from monolith architecture. We go deep into some of the reference architectures that we provide here at AWS Services. We'll design a retail application built on the principles of reference architecture, and we'll go over the components and feature set and followed by demo. Okay, to begin with, what are the characteristics of modern applications? So what are the characteristics of modern applications? So these applications can be in any industry vertical, known or unknown. For example, these can be from online business store, e-commerce, media, and online gaming. It could be cryptocurrencies or space technologies, things like that. However, when we are talking about modern applications, there are some unique characteristics for these applications. For example, there could be hundreds and thousands and even millions of online active users using your website real time and from any type of devices. And these applications themselves could be processing high volume and also high velocity of data, where it in turn process the data and provide the insights back to user in a really ultra fast response times ways, so that the users can take a informative decisions so quickly. And um, these applications has to be scaled to a higher degree, so that it supports the change in the data growth, and also change in the popularity of the users of the application, so that it attracts more users, things like that. So it has to be highly scalable applications. And also these applications, or building this application rather, support some kind of cloud native economics model. For example, you can start as slower, or you can start a smaller application, and then you can add the capacity as and when you're growing, again by data or request per second, things like that. And these applications should support high agility, which means they should support open source APIs, so that if the customers planning to create new features or things like that, they have the development of this application should support the fastest or fast phase of the development and testing cycle, so that the go to market window will be smaller, and then they reach as many customers as possible. So these are some of the characteristics of modern applications. Let's look at how traditionally the applications were built, and more specifically, let's make a case for migrating from monolithic applications to microservice architecture. Okay, to begin with, back in 60s and 70s, mainframes are the predominant way to build an applications. So when looking back from some 2000s, people characterize these type of building applications as single tier applications, and it lasts until like 80s. And when client server architecture were introduced, usually people refer that as two-tier architecture. And from that point onwards, that changes significantly how the applications were built. And when internet arrives in 90s, and as a result of that, the three-tier application architecture emerged, and which means your application will be are divided into 3 different tiers. Predominantly, we call them as UI layer, application layer, and also database layer. So in 3-tier architecture, for majority of the applications, the client and application layer can be distributed, although it's not necessarily all the applications were built that way. However, there is a flexibility for distributing your client and application code, and also scaling. So both of them were introduced in 3-tier architecture, yet your database layer is predominantly a monolith in nature. And this is pretty much the norm for building applications until 2000s. And on this presentation, of course, we are talking about modernizing applications, which means we are essentially advising for moving away from 3-tier architecture to microservices, which also referred to as multi-tier architecture. So let's understand what is the definition of monolith application in context to 3-tier architecture, and we talk about some of the disadvantages in this model, and talk about the advantages in microservices in next few slides. First, let's understand what is the definition of monolith kind of architecture. To begin with, a monolith architecture in terms of software engineering, it is defined as a single tier software layer in which the user interface, the business logic, the data access code all combined in a single program that actually deploys in a single platform. So this complete application with all the business logics across all the development teams in a given company will be tested together and deployed in one program in production. For example, if I take a retail website, there could be many different development teams developing different features in the retail website. However, once the development was completed, they actually tested together for all the services together and deployed together in a single platform, right? That's what the monolithic application means. And also, this application code base uses single kind of application code to interact with the database layer as well. I'm presenting in the screen the sample reference architecture for 3-tier architecture, where, let's say on left-hand side, if a user trying to access a retail website, in this example, from their desktop, the connection or the call usually lands in presentation layer, where essentially your code base still lives in some kind of EC2 machine. Following that, the request lands on business layer, where your entire code base again deployed in mostly in a single EC2 machine, or it could be multiple EC2 machines, where the call goes to EC2 machines to a load balancer for high scalability aspects of it. But the main point here is your code base is still mostly in a single monolithic kind of architecture, and that code base also has business logic to interact with your database, where your database is also is essentially a single database that will be used in majority of these cases here. So all in all, this is how a monolithic application will be represented using 3-tier architecture. And again, as you see here, because of this, there are some limitations. So yeah, as we talked a few minutes ago, because of the nature of this application, where we are building the whole different services, different components together, and deploying all of the code base together in one single platform, it's really hard to scale the application. For example, as you are building and deploying in one single platform, you cannot isolate different tiers. For example, you cannot isolate a database tier per se to scale just that component. You have to scale all the components. In many cases, you have to scale all the components together. You cannot isolate and scale differently. And also, because different departments or different teams code base is developed and tested together, it's really hard to isolate where the component fail happens, right? For example, if your code base is interacting with different services, or if there is a problem or some kind of error in one service, it's really hard to identify and narrow down that particular service which is causing problems. Majority of the cases, if there is an issue in this kind of applications, all the teams in an organization come together, troubleshoot it together and narrow down the where the issue is, and it takes time. And because of, again, by nature of this type of architecture, the options to choose the right kind of database or right kind of application layer or the programming language is really hard. You have to pick and choose one service that is that is more suited for all the services, right? So you may not have, you don't have many options to do that. And lastly, the fastest you can go and deploy in production is based on the slowest development cycle for any given team. So so it's not really sort of well suited for innovation kind of thing, where you have to develop your application fast and deploy the application fast, things like that. So these are the limitations. Now let's look at what are the what is microservice, how can we define services, and what are the advantages of it. So a microservice is defined as a loosely coupled, tightly scoped, independently deployable and scalable applications, which means, again, if I go back to my retail example, if I pick one team in the organization, the whole team, I mean, all of their code base and even the database connections, everything can resides within the team, which means they can create one or few of the services, and then they develop the business logics and they deploy the services independently of the other teams, right? And because of this, the it's easy to identify where the what is the service that was errored out, because it is, again, we are working in the scope of one team, and because of that, the blast radius is also very small. And um, and these are, as we can develop and deploy these services separately, we have this option to choose the right database and right application layer for my service. And I can even scale my application layer and database layer as and when needed, right? So these are all different advantages of this service. Again, the whole concept is coming from containerizing or tightly scoping your application and deploying your application independently, and that actually opens up the room for other innovations, and also make things will be much faster in this way. So let's look at the reference architecture, how this application, how microservice architecture will be built. So what I'm presenting in the screen is the reference architecture. We're not talking much about the user interface layer in this diagram. However, typically customers use something like CloudFront and backed by S3 for providing or responding back to the website in a static pages, things like that. But when it comes to the business layer, this is where the concept of breaking down your monolithic application to microservice application come into picture. For example, here in the screen we're presenting, instead of you're deploying your code in a EC2 based services, you can use a containerized applications. For example, you can use EKS, ECS, and also maybe Lambdas, right? So you can deploy your code in a containerized manner so that you can increase or decrease the capacity for that service, things like that. And because of that, you can choose different type of databases that are suitable for your business logic, right? So what I'm presenting on the screen is in database tier, we have Elastic Cache Service and also RDS, which actually using I mean they're being used in this example for different components or different containers.
Thank you, Vijay. Let's talk about building a modern retail website using the very principles we just discussed on microservices. So out of this, what we are going to do today is we're going to build a modern retail website, which will be using it for the rest of the presentation and, of course, for the demo. So what we need here is a rich user experience with a low latency, and, of course, the scalability and high availability with our microservices. So a user, when access our new website, should be able to register, log in, and browse the products in various categories, and should be able to add items to the cart and place the order. So these microservices, which we wanted to build, should be able to hyperscale automatically whenever there is an increase in users base, for example, significantly. And the number of requests, if they go up drastically on our new website. So these microservices should be elastically scale and should be able to automatically restart whenever there is a hardware failure. So as we discussed in previous slides, each microservice should have unique responsibility, and the CI/CD workflow for automated testing and deployment cycle that should make our microservices to be deployed very fast. So we'll be building microservices for various responsibilities. So one microservice we're going to use in the presentation layer, it's called web app. So which is a UI, user management. So where I can able to add the user, delete the user, or extract the user information. And similarly, a product microservice, which is responsible for product cataloging and management. A cart microservice that's responsible for cart management for a particular user. And order microservice should be responsible for order management. So it should be able to place the order, extract the order, etc. And for operational aspect, we'll be using two microservices, one for monitoring and alerting, and another one for order fraud detection. And in the database layer, uh, so let me move on to the next slide so we can talk about the database persistency layer. So here at high level, the architectural components for our retail website starts with Amazon CloudFront. So that will give us the low latency user experience we are looking for. And the microservices for presentation and business logic and operational. So that will be containerized and orchestrated through Amazon Elastic Kubernetes Service. So the containerized user and card microservices will be using purpose-built databases with Amazon MemoryDB for data persistency layer. And the product and order microservices will use RDS PostgreSQL engine for data persistency layer. So we'll discuss in detail in next slides on why we picked each purpose-built database service for and Amazon EKS for container orchestration.
Thank you, Krishna. For next few slides, let's look at our AWS services that we are using in this architecture. To begin with, let's talk about Amazon EKS, which is Amazon Elastic Container Service for Kubernetes. And to understand that, let's spend a few minutes talking about Kubernetes itself. So Kubernetes is an open source container orchestration system for automating, deploying, scaling, and managing application code. So Amazon Elastic Container Service for Kubernetes, which shortly Amazon EKS, is a managed service that make it easy for you to run Kubernetes on AWS without needing to be an expert in open source Kubernetes. So essentially, Amazon EKS orchestrate your business layer using this container service, where you can provide your definition. For example, you can start with saying how many containers of any given application you need, and also in which availability zones in a given region, things like that. You can create a definition of it, and Amazon EKS makes sure the definition is put in place. For example, if there are issues where one or two containers goes down for any reason, Amazon EKS manages it for you, which means it actually replaces the failed containers and make sure your definition is put in place at any given point of time. And also it makes it easy for managing aspects of it, which means the upgrade to a latest version, and scaling even your master and worker nodes, things like that. All of that will be taken care automatically for you. And Amazon EKS also support classic load balancers and application load balancers and network load balancers for scalability. And it can integrate with other AWS services. For example, it integrates with IAM for security, and EBS and EFS for storage, and so on and so forth. It does supports multi-AZ deployment for high availability. And by using federated deployments, you can extend the service for different regions as well. Let's talk about the second service in this architecture, and this is mainly the database service, which is MemoryDB for RDS. So MemoryDB is a fully durable in-memory database service. It is purpose-built specifically for modern applications which were built with microservice architecture. Let's dissect that a little bit. So why we are saying as this is a purpose-built service for microservice architecture? There are a couple of reasons. Number one, the MemoryDB is a fully durable service, and also it supports open source APIs for Redis, which means that it will provide agility because you can use open source products or APIs and build your application. And also it supports multiple data structures. Everything, all are in-memory data structures. For example, it supports strings, lists, sets, sorted sets, hyperlog logs, geospatial, and strings. So when we are building microservice architecture, there will be a need that we need to choose different type of data representation. In other words, different type of data structures that are suitable for those microservices. So MemoryDB does provide a wide variety of data structures, which could be suitable for or which for different type of application needs. And also, MemoryDB does support multi-AZ deployments as well. Let's talk about Amazon RDS for PostgreSQL. So to begin with, PostgreSQL is a popular open source databases for over 30 years, and the primary reasons for the popularity is it provides high performant database and also scalable database that matches commercial databases that supports commercial databases, and it supports wide variety of indexing type, partitioning, native JSON-based support, and also parallel processing. Amazon RDS for PostgreSQL is a fully managed service that supports or that's compatible with open source PostgreSQL, and also it supports the extensions like PostGIS, HStore, PGLogic, and PostGIS, etc. And when it comes to performance and also performing high performant applications, Amazon RDS for PostgreSQL is a very good fit because it supports up to 80,000 IOPS per second, and also it can scale up to 64 terabytes in storage. And for read scalability, it supports up to 5 read replicas in multi-AZs. And when it comes to security, the service can integrate with other AWS services. For example, it can integrate with IAM, and the service itself is deployed securely in a dedicated VPC. And also it supports features like KMS, which is encryption at rest, and also encryption at transit, and also it supports Kerberos.
Scaling. Thanks, Vijay. So let's look into the scaling aspect for our microservice and other various services we picked. So I'm going to begin with EKS scaling capability. So Kubernetes natively provides a rich set of capabilities that allows both traditional and modern workload types to scale dynamically based on consistent and declarative deployment model. So the Kubernetes cluster autoscaler, so it automatically adjusts the number of nodes in your cluster when the pods fail or are rescheduled onto other nodes. So the cluster autoscaler is typically installed as a deployment manifest in Kubernetes cluster. So it uses leader election mechanism to ensure high availability, but scaling is done only by one replica at any given time. So the cluster autoscaler, it's a tool that automatically adjusts the size of our Kubernetes cluster when either there are pods that fail to run in the cluster due to insufficient resources, or there are nodes in the cluster that have been underutilized for an extended period of time, and their pods can be placed into other existing nodes. The second one I would like to highlight is the Kubernetes horizontal pod autoscaler, so which automatically scales the number of pods in a deployment manifest using replication controller or replica set. Based on that, the resource is CPU utilization. This can help your application scale out to meet increased demand or scaling when the resources are not needed. And the third point I would like to highlight is the Kubernetes vertical pod autoscaler, so which automatically adjusts the CPU and memory reservations for your pods and to help right size your applications. So in addition to that, EKS supports elastic load balancing, which includes classic load balancer, application load balancer, or network load balancer. So with that, I'm going to move on to MemoryDB for the scaling aspect. MemoryDB cluster can be scaled horizontally or vertically with zero downtime. So Amazon MemoryDB can be scaled horizontally by adding or removing nodes, or vertically by moving to a larger or smaller node types. Amazon MemoryDB supports write scaling with sharding capability and read scaling by adding additional replicas. Amazon MemoryDB cluster continues to stay online and support read and write operations during the resizing operations. So you can create Amazon MemoryDB cluster with up to 500 nodes. So this will give you the maximum memory storage capacity of 100 terabytes. Let's move on to scaling from RDS PostgreSQL service point of view. So you can scale compute, memory, and storage with push of a button or using RDS API. See, for example, you can able to scale compute capacity in DBR5 machine class family for 12x large, so which will give you 48 virtual CPUs and 768 gig of memory with a EBS storage with 19,000 provisioned IOPS and within 25 gigabits per second network bandwidth. So in addition to that, RDS supports storage auto scaling. You can enable storage auto scaling for Amazon RDS DB instance if your workload is unpredictable. So with the storage auto scaling enabled, when Amazon RDS detects that you are running out of free database space, it automatically scales up your storage when free available space drops below 10% or 5 gig, whichever is greater. And the low storage condition stays at least for 5 minutes. You can modify provisioned IOPS for RDS instances and scale up to 80,000 IOPS in 1K IOPS increments, and the storage capacity up to 64 terabytes. And you can add up to 5 read replicas for scaling out read intensive workload for horizontal scaling.
Thank you, Krishna. So when it comes to performance, there are certain aspects in this architecture that we need very high performance. For example, if you remember the reference architecture for this particular application that we're building, the user and the cart are the two microservices that needs high performance. For example, think of this scenario where if a customer is trying to log into the website using user and password, we want to log in, or we need to provide the info. We need to take the information from the customer and log the customer in as soon as possible, and make it available for the customer to search for the orders in a faster way. And if the customer is trying to purchase something, he can add different items to the carts, and then we should have the flexibility for the customers to change and modify the cart in any different devices and things like that. So the performance aspects of this application is very important. That's the other reason we are backing this application with MemoryDB for Redis. So when it comes to performance for MemoryDB, because of the in-memory nature of this database, the response times are ultra fast response times. For example, MemoryDB does provide single-digit microsecond latencies for reads and single-digit millisecond response time for writes. This was tested out for different type of node types as well, and also MemoryDB does support ultra-fast Graviton 2 based instances as well. And when it comes to the scaling of number of reads, which in turn constitutes for overall performance, so the MemoryDB can support thousands to millions of reads and write operations per second.
Thank you, Vijay. So let's look into agility aspect. So with the EKS, the Kubernetes provides the container orchestration we already discussed in the previous slide, which is easier to automate and scale container-based workloads. So Kubernetes framework consists of controllers so that track at least one Kubernetes resource type. So it's a control loop mechanism that reconciles the state of the resource against declarative state of the resource. Best example would be like a thermostat in a room. So when you set the temperature, that's telling the thermostat about your desired state. So the actual room temperature is the current state. So the thermostat acts to bring the current state closer to the desired state by turning equipment on or off. So Kubernetes embraces the declarative DevOps paradigm. So it dynamically takes corrective actions for your applications based on resources desired state defined in the manifest versus its actual state or the current state, which makes your application resilient to component level failures naturally. So this makes the managed EKS a natural choice for container orchestration for our new retail website. With the CI/CD integration into EKS, this would reduce the time to build, test, and the deployment of our microservices for our new retail website. So it helps deploying our new website microservices more reliably, faster, less overhead, and more importantly, the blast radius. So with the microservices, if one microservice goes offline, our website is not affected. So the blast radius is going to be much smaller comparing with Monolith. So without the further ado, let's jump onto the demo. So before I go into the demo, I just wanted to explain how the architecture for our new retail website looks like using Kubernetes and persistent data stores. So now putting it all together for the demo to build our new retail website using microservices at scale. So we have discussed in previous slides about each microservice that should have a unique responsibility, should be able to scale, and should be highly available. So we are using managed Amazon EKS for orchestrating our newly built containerized microservices. So the Amazon EKS cluster has cluster autoscaler, which scales out worker nodes when there are pods that fail to run in the cluster due to insufficient resources. And when it comes to the presentation layer, we have built a microservice called web app, so which is the front end deployed as a Kubernetes deployment manifest with the 3 replicas. So a Kubernetes deployment, it provides declarative updates for pods and replica sets. So you describe the desired state in a deployment, and the deployment controller changes the actual state to the desired state in a controlled rate, at a controlled rate. So in addition, we have defined horizontal pod autoscaler for scaling out pods when the pod CPU utilization goes over 50%. So it automatically scaling when the load subsides. So this is fronted by an application load balancer in our case, as you can see. And in the business logic layer, we have built user, cart, product, and order microservices. And each microservice is deployed with 2 replicas and using the deployment manifest and with the horizontal pod autoscaler to scale out these pods based on CPU utilization. And they are fronted by cluster IP load balancer. And microservices user and cart will be using Amazon MemoryDB, which is a purpose-built database for the data persistency layer. And the order and product microservice is using Amazon RDS PostgreSQL in data persistency layer. And the most importantly, I would like to highlight before I move on to the demo is Amazon RDS proxy. So in our architecture, we are using RDS proxy, which is a fully managed, highly available database proxy for Amazon relational database services. So that makes your application more scalable, more resilient to database failures, and more secure. So many applications, including those built on modern and serverless architectures, can have large number of open connections to your database server. So, and they may open and close database connections at very high rate, exhausting your database memory and compute resources. So Amazon RDS proxy allows applications to pool and share connections established with the database, improving database efficiency and application scalability. RDS proxy, it minimizes application disruption from outages affecting availability of your database by automatically connecting to a new database instance while preserving the existing application connections. So when failover occurs, RDS proxy routes the request directly to the new database instance. So this reduces failover times for RDS and Aurora databases by up to 66%. So going back into the visibility layer, in the visibility, we have using EFK stack, which is Amazon OpenSearch Service, FluentBit, and Kibana. So which consists of. So FluentBit is an open source and multi-platform log processor and forwarder, which allows you to collect data logs from various sources, that including the sources from Docker or the Kubernetes environment. And they send them to multiple destinations. In this case, we'll be sending the content to Amazon OpenSearch Service. So Amazon OpenSearch Service, it's a fully managed service that makes it easy for you to deploy, secure, and run OpenSearch cost effectively at scale. With that, we are using Kibana. It's an open source front-end application that sits on top of Amazon OpenSearch Service, providing the search and data visualization capabilities for data indexed in OpenSearch. So with that, I'm going to jump on to the actual demo. Yep. So let's go by. Before I start, I just wanted to explain. I just wanted to walk you through the setup, how it looks like. The setup consists of, we talked about Elastic Kubernetes Service, auto-scaling groups, and horizontal part autoscalers for various deployments in Kubernetes. So let me start showing with what the clusters, how the clusters are set up in our EKS environment. So EKS CTL, it's an open source utility which you can use to communicate with the Kubernetes clusters. So in this case, you can see I have defined a cluster named EKS CLU in the region US East 1. And the second one I wanted to show you is the node groups and the nodes that are part of, the worker nodes that are part of managed EKS. So what you're seeing it is the node group, which is using auto scaling group and with a minimum size of 4 and it can scale up to 8. And with the instance types, it's using T3 large. And if you can describe the auto scaling group, how it looks like on what conditions it's going to scale. So what you're going to look at is, see, the minimum size for the auto scaling group, you can see here is 4. The maximum it can scale up is to 8, and the desired capacity is 4, and the default cooldown period is 300. So it's going to look at, so whenever, as we discussed in the previous slides, right, whenever there is a pod, it couldn't be scheduled due to insufficient resources, that's when auto scaling group is going to take an action and add worker nodes. And let's look into our manifests, which is the microservices we deployed, part of our retail web application. So what you're looking at is various manifests that are defined in a namespace called Oak Tank, which contains all the microservices that relate to operating our retail website. So at high level, you are looking at a bunch of pods. So a cart deployment, which is coming from cart deployment manifest, and it's spin off two replicas for the cart pods. And then similarly, we are looking at order deployment, product deployment, user, and the front end presentation layer, web app deployment. And then we're also using a bunch of services. Our web application is fronted by application load balancer, so which you are seeing here. And other business logic microservices are fronted by cluster IP endpoint. And in addition to that, let me. There is also we are using we are using a FluentD, which is collecting the logs from all our Kubernetes pods and sending the logs to Elastic Search Engine. And this is our Kibana dashboard. We are using it for the visibility. As you can see, pretty much all the logs are being uploaded here. So you can able to debug or build a dashboards in Kibana for efficient troubleshooting. In addition to that, you can even do the integrations with PagerDuty. Let's say suddenly there is the traffic in your website goes up significantly, like tenfold, 100-fold. So you want to get notified. So you can able to implement the integrations into that. And so I just wanted to show the database layer side. So this is how, so the RDS PostgreSQL is fronted by RDS proxy. This is for high availability and connection pooling and multiplexing we talked about. And similarly, we have Amazon RDS Postgres engine. So that's for data persistency layer. So this is which is using DBM file large, and the engine version we are using is 11.13 with the multi-easy set to true, and the storage layer we are using GP2. And as for MemoryDB, we are using so this is our Amazon MemoryDB cluster. So we are using a number of shards 3, and we are using the node types of DB R6G large, and that's the cluster endpoint, and engine version is 6.2. And if you notice, in both the cases, we have enabled auto miner version upgrade to true. So that means AWS is going to manage automatic miner versions upgrade for you during the scheduled maintenance window. And finally, what is the website we built on? So let me show you that screen. So this is our e-commerce website. This is how it looks like. You remember we talked about the user. Whenever you register the user, so automatically it should communicate with the user's microservice and should be able to, and that in turn uses MemoryDB for data persistency layer. So let's start with that one, right? So I'm going to create a new register user. So I'm going to say some test12, some arbitrary number. So I mean, I haven't put any validation here, just to show the whole workflow. So now that we registered test12 user, so you can able to log in with the test12 user now. So once you log in, sorry about that. So let me try the test 11. Yeah, here we go. So it looks like I did not register the user properly for test 12. So, but I did create the test 11, register the test 11 user just before the demo. So once you log in the test 11, so basically the users, see this part of user section, it's interacting with user microservice, which in turn interacting with the MemoryDB for scalability. And similarly, we have the cart where you can able to add any products you want. And so that should be communicating with cart microservice. So this is the one, right? This part goes into cart microservice. So, and this cart, what this should make it is, our microservices stateless. What I mean by that is, for any reason, let's say I put some items in the cart, and our microservices dies for some reason, and the deployment manifest automatically going to restart these microservices in a new node or new other available worker nodes. So when it restarts, it still needs to, the cart state still needs to be maintained, and obviously it does. So if I open a incognito window, and let me show you that, or I can delete the pods. You know what? Let's do that. Let me delete the pods, and then I'll show you how the state is maintained within cart microservice using MemoryDB. So what I'm doing here is I'm deleting the pods I'm deleting, okay, kubectl, delete pod, and what we wanted to delete is in Oaktank, the label is service equals to cart. So that's the service we wanted to delete both the pods. So when you run that, you can see here, both the pods are deleted. So what it's going to do is it's going to restart new pods automatically. Remember, we talked about it. The way deployment manifest works is underneath, it's going to use the controller loop, which is going to check the declarative state and check with the current state. And if the current state, in this case, the pods are deleted, it's going to automatically reconcile. So that means it's going to restart the pods automatically. So if you can see here, so what I'm doing is I'm extracting all the pods in Oaktank namespace with the label service equals to cart. You can see both the pods are restarted. So when I restart, and if I go here, and if I come back, my cart state should be maintained. As you can see, essentially we made the services, our microservices stateless in this case, right? And the second demo I wanted to highlight is by inducing bunch of requests by scaling out the number of requests coming to our website and see how the pods are automatically able to scale. So what I'm going to do in this case is I'm using a utility called Apache Benchmark Utility, AB. And with that, what I'm going to do is I'm going to use the number of clients 50, which are going to process 100 requests and up to 300 seconds. And it's going to it's going to execute this particular URL, so which is going after our website and looking into fashion category in the product section. And once we run it, so this is going to run a huge load on our website. So while it is running, so what we'll do our Kubernetes, and we'll watch out for web deployment pod, how the CPU is gonna CPU utilization is gonna show up on our web deployment pods. And you can see here, so currently it's at 8% CPU utilization, and the target I set to 50%. So what I mean by that is whenever the CPU utilization goes beyond 50%, it should start automatically scaling our pods, which is the horizontal pod autoscaler we talked about. So it's currently at the 41%. Now you can see it went up to 56%. So now you should start seeing the number of pods are automatically scaling out for us. So with the second attempt, whenever it sees above 50%, so slowly it is going to increase by one pod at a time. So now you can see the number of pods went from 2 to 3 replicas here. And similarly, you can get it from here also. Get pod. Remember we talked about -n work tank and a label service equals to web app. And you can see currently there are 3 pods running, right? So we only deployed actually 2. So now the CPU utilization at 15%. So as I said, right? So when the load subsides, it automatically scales down the number of pods back to the desired set, which is 2 in that case. And I just wanted to show you how the horizontal pod autoscaler is set up in our Oak Tank retail website. So what you're looking at is this is the HPA we have set up, and you can see pretty much all the HPAs are using for the cart, order, product, user, and web app microservices, which are set it targets 50% CPU utilization. When it goes beyond that, obviously it's going to start scaling it. So that's the point I want to probe. And similarly, so this is the front end layer, right? We talked about. Now let's talk about the REST API layer. Basically the business logic layer. So same thing, right? And what I wrote was a simple code, which is in a Python. So all it does is, so let me show. So in this case, all it does is it's going to spin off 10 worker threads and calling order microprocess. For example, let's say you're having a huge sales event and the number of orders going up significantly, for example. So how our order management platform looks like, how it's going to scale, right? How our database is going to keep up. So basically that's the idea in this case. What I did was a simple Python program. It's going to open a REST API thread to our internal microservice, which is order. And with the 10 threads, so I'm going to use 7 different terminals. So each terminal is going to execute 10 threads each. So it's like, so almost we are simulating of 700 concurrent connections to threads to our microservice and show at a minimum scale to show, how the pod is going to automatically scale for order microservice. Okay? So let me run this. So while it is running, so I'm going to do pretty much all 7 windows and kick off the same. So now we started running Oak Tank order test. So I used all 7. So now what I'm going to do is I'm going to use. So what we are using is the Oak Tank test order, which is going to spin off 10 threads, and each thread again is going to use 50 concurrent threads within each pod that makes connections to the database. So microservice called order deployment. So we are going to use 7. So we are going to almost 7 times the workload. So you can get when it comes to the workload, I'll show you that the number of requests on order service, how it looks like from the visibility in Kibana, right? So whenever we are kicking off that load, so our order management service should be able to automatically scale, right? So this is to tackle, let's say you're doing a major event and releasing a new product, and you're expecting user growth, for example. Suddenly we are going to look at significant spike in order placements or order management. So our service should be able to dynamically scale, and the database should be able to handle without any outage. So this demo is going to pretty much talk about that. So in this case, I used almost 7 terminals to execute the workload on order management service. So while it is in progress, as you can see, so the pods, when it started, it was only using 2% CPU utilization and had minimum number of pods 2, and the replicas it were 2 actually. So the minute when the CPU utilization went to 73% consistently, so immediately horizontal pod autoscaler spun off one additional pod, and the overall CPU utilization dropped to 50%. So which is little below the threshold we set. So it is operating. So the minute if you see more connections coming in, it's going to scale automatically up to 10 pods we define in our manifest. And the next one I wanted to talk about is so we talked about the stateless card management. So the next one I wanted to talk about is user requests, how it looks like from the MemoryDB. You remember we created a user, cancel this, and when you quit, so basically Kubernetes exec. So what I'm saying is, basically I would like to connect to one of the pod in card deployment in namespace OakTank, and I would like to execute a curl command. So remember we talked about, for all business logic microservices, we are using cluster IP endpoint, not a load balancer. So which is the reason I need to connect to one of the pods to be able to query the cluster IP endpoint. So what I'm doing is I'm using a REST API, I'm giving a REST API call to a user microservice, and I'm asking it to give me the user with the email test10.com. See, so it's going to give you the information what you need, right? And so this is the REST API call. And similarly, I wanted to do one final one with the database failover. See, what happens when the database fails over? So that's the one we wanted to test out. So it should be transparent. Okay. What I'm going to do is I'm going to run one of the workload test. So what this is going to do is okay. So what we are doing is we are executing again. We are connecting to OakTank test deployment to one of the pod in namespace OakTank, and executing a REST API call to run product test using 5 threads and 600 for 600 seconds of duration, up to 10 minutes. So this is the simple container we built for testing our product to see how effectively it scale, part of the CI/CD integration. And so while it does that, while executing the workload, what we're going to do is we are going to fail over the database, right? So now the workload started. So what I'm going to do is not just one place. Let's execute the workload from multiple windows so that you can see. I'm using almost 3 windows to execute the similar workload. So it's going to use 5 threads from each, so almost 15 threads, and execute for 10 minutes. So while it is doing, so let's go back and do the RDS database failover. So what I'm doing in this case is I'm going to use AWS RDS API to CLI to reboot the instance with the failover of our RPG RDS PostgreSQL instance. So this is going to do the database failover. So once it fails over, so what we can do is you can look at the log files from the pods. So with the kubectl logs deployment. So what we are doing is, so while we are executing our threads against product microservice, you can see how the requests look like. You can see, right, all the requests are coming, majority of them with the status code 200. So the idea we wanted to prove is whenever the database is failing over, what happens? Typically, right, with the RDS proxy I talked about. So with the proxy, during the database transition, role transition, it's going to retain the existing connections and automatically it will reestablish the connections as soon as the failover is done. So for you, so that means application doesn't have to worry about reconnecting to the database whenever there is a failover instance. So let's look at if our failover is completed successfully. So I'm going to use RDS API, RDS CLI with the describe events that will show us
whether the failover request processed or not. As you can see here, the instance failover is completed for multi-AZ, and the user requested for the failover of the DB instance. Right? So the failover is completed. So let's look at Kibanas to see if there are any failures during the failover. Remember, we talked about in the Kibana dashboard, we are sending all the logs. So I wrote a simple query. Let me go back to the Discover. And in the Discover, I'm going to open. So one of the query we wrote for product. So if you look at the product request, what it is doing is, it is filtering down by the namespace OakTank and with the labels product. So that means I'm only looking at the logs from product pods. And then the log process response status exists. So that means if there is any status that is not 200, so which is failed, I'm interested in it. And the status is not 200. So as you can see, there is absolutely none. So that means no single request failed. So what I mean by that is, if you look at the contents, right? If you look at the contents, you can pretty much see pretty much everything is going through, right? Almost we're getting like 6,332 hits. So 2,000, almost we're getting the rate of 2,000 requests per second. That's the rate we are getting. And similarly, you can also build it. Remember, we talked about building the dashboards. So this is the dashboard that talks about whenever we ran that RDS microservice using a bunch of applications, you can see we reached almost 120,000 orders per second rate, and our service was able to scale without any problem. Same thing, if you open, let me open another one. I'm going to go to visualization layer, and I created one more dashboard for our products also. So you can see here, OakTank product request by time. So even in the products, you can see it went up to almost 80,000 requests or 8,000 requests per second, and we failed over the database in the meantime, right? So our data, so you can see our microservice can able to seamlessly handle the database failover without any errors from application point of view. And so that pretty much brings down to the conclusion to all our demos. So in this one, right, the takeout from here is the microservices whenever you are designing. So keep the principles in mind what we discussed, about the scalability, availability, and automatic failover. And each microservice should have unique responsibility so that you can able to utilize purpose-built databases for the corresponding microservice. And part of the demo, we demonstrated the scalability of, we looked into the scalability of worker nodes, and we demonstrated horizontal auto scaling for our web application. Whenever we have increased the load, our web application presentation layer can able to scale. And similarly, we demonstrated the stateless pods, using cart management. We deleted the pods for the cart, and the Kubernetes deployment manifest automatically created the pods, and you could see the carts, items in the cart did not disappear. Right? And the third one we looked into is the scalability of business logic microservices. One, we looked into the order management. So whenever there was a major event, if the number of order requests goes up, the service can able to scale. And in addition to that, so if somebody is querying the product catalog extensively, we failed over the database, and we demonstrated that absolutely there is no one single failure from the application point of view during the database failover. So we have looked into the microservices principles. We have demonstrated how horizontal pod autoscaler or autoscaling group in AWS Kubernetes cluster that can scale our pods or worker nodes independently. We looked into that. And we have demonstrated the capability of, we induced the synthetic workload on presentation layer, and we showed you how the presentation layer was scaled. And similarly, we induced the synthetic workload into order management service, and we were able to show you how that microservice was able to scale. And finally, we failed over the database and showed you how RDS proxy can help you minimize the failover time, and as well as don't have to worry about reconnecting to the database whenever there is a failover incident happens. Proxy will take care of it for you. And similarly, we looked into the presentation layer. We looked into Amazon Open Session Managed service, how the log content looks like, how you can use it for troubleshooting, or the presentation of the alerting part of it. So with that, I'd like to move on to Q&A and take any questions if you have. Thank you very much.